We've learned a lot about sets and how to work with them. One of the purposes of sets is that they are basic data structures. In fact, every data structure you learn about in computer science comes from the idea of a set. But we have data structures not just for holding information, but for doing something with it, and that's what we're going to dive into next. At the core of computer science is the idea of taking objects from one data structure and then assigning them to objects in another data structure. For example, this short Python program takes natural numbers and assigns them to another natural number using a mathematical formula. This one takes natural numbers and assigns them to strings by duplicating the string foo a number of times equal to the input. This Python program takes strings, on the other hand, and turns them into natural numbers by computing their lengths. And this one takes two strings and assigns a Boolean true or false value according to whether the first string is shorter than the second. The idea that threads all of these programs is that they take input from one set and then assign it to output in another set. In Python, we call these programs functions, and in fact that term is taken from a bigger and older term from mathematics that we're going to use now in a formal definition. So let's define a function to be a rule that assigns elements from one set, which we'll call the domain of the function, to elements of another set, which we'll call the codomain, in such a way that every input is assigned to exactly one output. All of the Python functions we just saw fit this definition. In the first one, the domain and codomain are both the set of natural numbers, and the rule is this mathematical function that you see in code. In the second, the domain is the set of natural numbers, and the codomain is a set of all strings. In the third, the domain is a set of strings, and the codomain is the set of natural numbers. And in the last one, the domain is the set of all pairs of strings, and the codomain is the two-element set true-false. Here's a function that isn't in code. This function is called f. The domain is the set of real numbers, and the codomain is also the set of real numbers. There are many possible functions between these two sets, and so I need to tell you what the particular rule is. The rule I have in mind is that given an input, x, we will square it and add 1, and that's the output. And here are some examples of this function in use. This should remind you of predicates. In fact, every predicate is a function whose codomain is always the set of Boolean values true, false. For example, earlier we looked at the example of the predicate q of x, whose domain is the set of integers, and each integer is assigned a true, false value based on the outcome of the statement x mod 3 equals 0. This is a function from z to true, false, and the output is determined by taking an x, plugging it into this statement, finding x mod 3, and seeing if it's equal to 0. There's a number of different ways to represent functions, and they're all good as long as we know exactly how to assign elements from the domain to elements of the codomain. Functions given as mathematical formulas do this by telling you how to compute the output. Predicates do this by giving you the logical statement to evaluate. But we can do it in other ways as well. Especially useful if the domain and codomain are finite sets is just a simple diagram, which is like a spreadsheet that pairs off the inputs with the outputs. This diagram, for example, gives a function f from the set 1, 2, 3, 4 to the set x, y, z, t, such that f of 1 equals y, f of 2 equals x, f of 3 equals z, and f of 4 also equals z. Sometimes it's also given as a kind of matrix with big parentheses on the sides. In Python, basic programs are called functions, but we can also represent generic functions using the dictionary data structure. The dictionary in Python is set up exactly for this kind of purpose, to make an explicit connection between elements of one set and elements of another. Here, for example, is the function we saw in the last slide written in dictionary form. We can even use function-like syntax using square braces instead of parentheses to see that f of 1 equals y, f of 2 equals x, and so on. There's two nuances about functions we need to discuss before moving on. First, the definition of a function says that it's a rule that assigns elements in the domain to elements in the codomain in such a way that every input is assigned to exactly one output. What does that phrase at the end mean? Every input is assigned to exactly one output. Well, it actually means two things. First, it means that every input is actually assigned to at least one output. There can't be any input that simply doesn't get assigned or gets assigned to something that isn't actually in the codomain. For example, look at the mapping f from the natural numbers to the natural numbers defined by the mathematical formula f of n equals n over 2. This looks like a function, but it's actually not, because if you plug in n equals 5, you get 5 over 2, but that's not in the natural numbers. So this is not a function from n to n, because if we define it in this way, with this particular codomain, the outputs must be natural numbers, but sometimes are not. If you tweak the definition to say the codomain is R, the real numbers, then this is a function. Or look at this mapping given by a diagram. This isn't a function because the number 2 has no output at all. So every input must actually have an output that belongs to the codomain. But the definition also says that an input maps to exactly one output, and that means it cannot map to 2 or more outputs. For example, look at this diagram. That's got the same domain and codomain as we saw before, and it's still not a function. This time, the number 1 maps to 2 different outputs. Just like a computer program, we wouldn't want a situation where one user input leads to 2 different results. The second item is also about the codomain. The domain is the set of all the allowable inputs of a function, but while the codomain has to contain all the outputs, some of the elements in the codomain may not actually be outputs. For example, look at the function f from the real numbers to the real numbers given by the formula f of x equals x squared plus 1, which we looked at earlier. The codomain is the set of all real numbers, but not every real number will actually be an output of this function. For example, 0 is not an output of this function because x squared plus 1 is always a positive number no matter what the input. And in this finite example, the set x, y, z, t is the codomain, but not every element of the codomain actually has something mapping to it. So we're going to define the range of a function to be the set of all the actual outputs of the function. That is, in set builder notation, the range of the function f from a to b is the set of all points b in the codomain of f such that f of a equals b for some a in the domain. Again, it's the set of all points in the codomain that are actually output by the function. In some cases, the range and codomain are the same set, but in other cases, the range is a subset of the codomain, but not equal to it. The codomain of a function, in other words, is sort of like the data type of the outputs. For example, that function f from r to r given by f of x equals x squared plus 1 has outputs whose data type is real numbers. But not all real numbers are actually produced. The set of real numbers that actually does get produced is the range. And in this case, if you're wondering, that's the set of all real numbers greater than or equal to 1. Likewise, the range of this function is x, y, z, because those are the actual outputs of this function. T is never output by anything. So this video was an initial deep dive on the very central idea of the function. You've learned what a function is, about its domain, codomain, and range, how we represent and notate functions, and how a mapping between 2 sets can fail to be a function. In the next 3 videos, we'll briefly look at 3 properties of functions that refer to how it maps points from the domain to the codomain.